Thank you very much. So this is a study conducted at my previous affiliation, mostly headed from Emily Finn, and I have nothing to disclose. So layer-dependent fMRI is getting popular, and while it started on primary areas, it has really taken off to higher cortical areas too. However, there's still a lot of white spots on the map here. For example, on the frontal lobe here, such as in areas like the dorsolateral prefrontal cortex. And although those areas have very specific functional microcircuits. For example, there are these different types of cells. We have like cue cells, delay cells, response cells that eventually trigger the motor system. And each of them are located in different cortical laminae. And Emily Finn found this old task that is supposed to engage these different cells differently. For example, showing participants strings of letters and then cue them to either memorize these letters and keep them in their working memory in the order they saw them, or sort these letters according to an alphabetical order in their mind, which is believed to mostly engage the superficial layers. Later in the task, they are shown random letters within that string, and then the participants need to do a response decision, which is mostly believed to engage the output layers. And this simplified view of the microcircuitry here really nicely explained all the results that we saw. For example, zooming into a CBV-weighted EPI that has this inherent T1 contrast, you can see that the response activation really nicely follows the deeper layers of the cortex along this cortical ribbon here after a bit of smoothing within cortical layers, whereas the alphabetization condition really nicely follows the superficial layers parallel to the deeper ones. And this might be even clearer visible in the group results of 14 participants in the time courses, where you can see that the superficial working memory layers, they shoot up as soon as the participants start with this alphabetization, and when they found a solution, it goes back. Whereas the deeper output layers, they don't really care much about this alphabetization. They almost stay at baseline and only shoot up when they have found a solution and need to do this response decision. And if you are interested about the neuroscientific implications of that, check out Emily's preprint here, where she talks about them also with respect to the working principle of DLPFC in humans. For the remainder of the talk now, however, I would rather like to focus on the fMRI acquisition challenges and talk about how we get these data in the first place and share a few lessons that we learned along the way. So the first big challenge was to find the ROI, because it doesn't really have clear anatomical landmarks that are consistent across participants. So we used this functional localizer with real-time analysis directly at the scanner console. And based on this location, we then followed a two-pronged approach with a medium-high resolution axial protocol and a high-resolution sagittal one. And when you can zoom in here, you see that actually in both of them, we have indications of layers in both of them. Whereas the axial one is just barely sub-millimeter, we have at least like two independent layers and a lot of different task conditions, whereas for the axial one, we have up to like 4 or 5 independent voxels across cortical depths, but only 2 task conditions. With these large matrix sizes, we had some challenges, specifically considering that we use a 70 with low bandwidth, and we are using this body gradient where we have these acoustic resonances along the frequency spectrum. And the gradient amplifiers actually would allow us to go to EPI switching rates up there, whereas the PNS just limits us. And so we are kind of stuck to end up being very close to these acoustic resonances. This means that we have B0 sensitivities and phase offsets that can be challenging when you want to use partial Fourier with Pox reconstruction. So we have these like characteristic black holes that you wouldn't have for zero filling, but then we would blur our data, which we didn't want to do. Across all the participants, we kind of had to play around with the phase encoding direction and the shim values to get rid of these phase interference patterns, or at least shift them to areas that we don't care so much. Also, across every participant, we had to adjust manually the grappa kernel size and the regularization strength to get rid of these infamous grappa artifacts. And we were also fighting with physiological noise introduced and task-locked artifact levels. For example, for these very engaging working memory tasks, participants sometimes had these deep breaths of release after they were finally done with this exhausting alphabetization task. And during the intense task conditions periods, they had a more shallow breathing patterns, resulting in artifacts like that. So adjusting so many parameters on an individual subject basis brought us into this weird position where we needed to decide where we stand on reproducibility versus heterogeneity, or data quality versus data consistency. Because like the current data sharing standards really dictate that you acquire your data in a very homogeneous fashion. And for us, this was only really possible in a McDonald's kind of way, where you get super reproducible results. It's the same in summer or winter, however, lower quality. Whereas when we can manipulate them on an individual subject basis, we get consistently higher quality at the cost of like homogeneity. And I'm not saying that these standards are a bad idea. I'm really in favor of them. I only want to say here that we couldn't really achieve both of them at the same time. So we found a compromise to keep the most important parameters constant, like echo time and resolution, whereas adjusting a lot of other parameters, for example, bandwidth or most of the reconstruction parameters. I also would like to share some lessons that we learned about the applicability of event-related designs with layer fMRI, specifically with respect to the unique frequency features in layer-dependent fMRI data. So for conventional fMRI, like HCP-style data, you usually have frequency spectra like that, where we have these respiratory peaks and maybe aliasing of that. And at low frequencies, we have this 1/f noise that we usually take care of with drift corrections. For layer-dependent fMRI, it's slightly different in the sense that we can obviously not interpret these higher frequencies, simply because we don't have the TRs for that. But we can also not really interpret this medium frequency regime either from like 5 to 15 seconds, because we don't have reasonable assumptions about the canonical HRF. We know that upper and deeper layers have different HRFs that we would need to deconvolve our data. And this is mostly coming from the different like vessel contributions of the upper and deeper layers, meaning that any kind of activity changes in this frequency domain is probably coming from the vessels, and we cannot really assume that it's coming from the neurons. On top of that, we can also not really use the lower frequencies either, because we have this amplified 1/f noise, because we are forced to use low bandwidth and are therefore more sensitive to these low frequency like field offsets. So we end up with this very tiny frequency window to encode our task. And for conventional, random, event-related, like balanced task designs, you switch back and forth between different task conditions, sometimes more frequently, sometimes less frequently, simply because it's random, right? Meaning that a lot of variable like signal power actually leaks into these like bands that we cannot really interpret. And you can barely separate the signal from the noise. Whereas when we manually reshuffle them so that they are less random but fit into the frequency window, then we can much better separate the signal from the noise. Another lesson that we learned that is almost embarrassingly simple refers to the fact that we can have noise amplification for these like noise-driven submillimeter data along the analysis pipeline. So you all know that 1/A plus 1/B is not the same as 1/A plus B, meaning that the average of relative signal changes is not the same as relative signal changes of average signals. Or in other words, you get usually lower signal change response if you take your runs, average them, and extract your signal, versus when you first extract your signal and then average that result. Simply because we can have noise amplification of this denominator here. So we learned from that it's really beneficial to average the heck out of it before you start to do any signal extraction. For example, we average across runs, across trials, across contrasts, across trial blocks, across voxels within layers, and across neighboring time points before we even start to like normalize our signal. And you can see here that we can much better separate the two upper and deeper layers if we average later compared to earlier. Another challenge that we had to face was to interpret the relative cortical depth with respect to layers. So we followed Bob Turner's postmortem calibration approach, where we use any cadaver brain sample like the Ding Atlas or the big brain to identify features across depth that are also visible in high resolution in vivo like iron or myelin weighted or functional data. For example, this peak to dip feature that seems to be somewhere between layer 4 and 5, and then we can interpret our functional results with respect to this landmark as two like subsets of layers, everything above layer 4 and layer 5 and deeper. So in conclusion, upon dealing with all these challenges, we do end up with neuroscientifically interpretable results that are very consistent across participants, especially in VASO, where you can see that the deeper layer, we always have this kind of response profile, whereas the upper layers are always green. They are always more sensitive to this alphabetization. And with this, I thank all my colleagues and foremost my co-author, Emily Finn here, and I thank you for your attention.